The term quantum computers is a buzzword these days. Everybody talks about them, although few know what they actually are. In this video, I'll explain what a quantum computer is and how they work. Quantum physics is a whole set of theories and ideas that go right against our common sense and intuition. One of these theories is the idea of a superposition, the idea that a particle can be in multiple places at once. This doesn't make sense, does it? This apple, during its flight, was only in one place at once. How can something be in multiple places at once? I've never seen someone both inside and outside at the same time. Have you? Superpositions were first described in Thomas Young's 1801 famous double-slit experiment. The experiment can be broken down to three main parts: bigger microscopic particles, waves, and smaller microscopic particles. Let's look at microscopic particles first. An example would be a baseball. You pitch a baseball toward the home plate. If the baseball made inside the strike zone, it would land on the cage. Now, if you add a barrier in the baseball diamond into the hole for a strike zone and turn on a pitching machine, you would see that the baseballs only land on one stripe in the middle of the cage. If you add a second hole, you would see two stripes instead. Now, let's look at waves, the second part of the experiment. An example would be water waves. With a similar setup, we can see a unique property of waves. If we throw the waves, so to speak, in one slit, we see a diffraction pattern at two slits and interference pattern. The waves spread out and the peaks and troughs come together or cancel each other out. Finally, we can look at the last part, microscopic particles. They're particles, so they should behave just like baseballs, not the waves, right? Let's look in more detail. We can shoot electrons at the setup. With one slit, we can see one stripe just as we expected. However, with two slits, we see a new pattern, the interference pattern for waves. What? The electrons, tiny particles, behave like waves. The physicists looking at this experiment were confused, as you should be as well. What happened to the electrons? Which slit did they actually go through? In order to answer that question, the physicists decided to peek at the electrons by putting a measuring device on the slits. And as we expected, electrons passed through each slit half the time. However, when the physicists looked at the screen, they found that the electrons had stopped being like waves and produced the same pattern as the baseballs. What happened? As it turns out, the observations made by the scientists made the electrons choose to act like particles. It's like the electrons were aware that they were being watched and decided to act differently. More importantly, when electrons are not being observed, they behave like waves. In that case, it becomes impossible to pinpoint the location of the electron. Given a wave, can you tell me exactly where it is? The uncertainty of where the particle is at the moment is an example of superposition. Other properties of particles can also be in superposition, such as spin, which is what we are using for our quantum computer. All particles, including electrons, have a property called spin. No, particles do not actually spin, but they act like they do. When measuring the spin of a particle, it can either give spin up or down. However, before measuring the spin of a particle, we don't know what it is, so it is in a superposition, where if you measure the spin, sometimes it gives spin up and sometimes spin down. Quantum computers are based on the classical computer, so we need to briefly discuss one more topic before discussing the quantum computer, the classical computer. These work by sending electrical signals through transistors, gates, and so forth. These electrical signals are bits and can either be a 1 or a 0. With 2 bits, there are 4 possible combinations. 20 bits contain more than 1 million combinations. However, a group of 20 bits can only represent one combination at once. A classical computer would have to store 1 million different numbers in 1 million sets of bits. And to search for one number from the 1 million numbers, the computer has to go through them one by one. Quantum computers use particles in superposition instead of electrical signals to represent each bit. In order to represent 1 and 0, we can assign spin values to each. That is, 1 is represented by spin up and 0 by spin down. Keep in mind that the particle is in a superposition and thus able to represent both 1 and 0 at the same time. The raw computing power of quantum computers is due to what we explained earlier, the superposition. With 20 quantum bits, or qubits, we are able to represent all 1 million combinations at once with one set of qubits. If we built a quantum computer with 400 bits, it will be able to represent more than 10 to the power 120 numbers all at once, more combinations than are possible moves in a game of chess. Due to the superposition representation of numbers, quantum computers can manipulate multiple numbers at the same time, completing multiple calculations in parallel. For instance, asking a classical computer to find your favorite Pokemon will require to search through all 721 Pokemon until it found the right one. However, with a quantum computer, it will be able to search multiple paths at once and find the right Pokemon quickly. Remember how the superposition of the electrons disappeared when we measured them? A quantum computer will measure the spin of particles to find the final answer. What does this mean for us? It actually matters quite a bit, since quantum computers can hack our most complicated and secure password in mere minutes. They can also be used to simulate complicated molecules to bring new medications and counter much faster.